Okay, this time I'm recording. As I promised in class, here I am trying to solve two of these epicyclic gear kinematics from the last slide in the gear kinematics lecture slides, if you remember. I'm going to solve the D and J parts of that in that list. So this is the question. This is question D from that list, and I've already marked some of these stuff for you. So here we have 7 gears. Gears 3 and 4 are on the same shaft, part of the same rigid body, as are gears 5 and 6. They are part of the same rigid body as well. So the question, you might be thinking about what the question is here. The question is, let's say we our inputs are to gears 1 and 2. So sorry, 1 is not the gear, 1 is the carrier. So let's suppose we are setting the speed of the carrier, the angular velocity, when I say speed, of course, and the angular velocity of 2. We are setting those two things, and we want to find what is the angular velocity of gear 7. Okay, let's suppose that's what we are after. So in short, I know what omega 1, omega 2 are known, and unknown omega 7. Okay, so let's start to work on this problem. And of course, as we always do when we are confronted with a gear problem, we match the velocities of the meshing gears at the pitch points. So the pitch point between gears 2 and 3 are labeled here as P2 and P3. Similarly, the pitch points within gears 4 and 5 are P5 and P4 and P5. The pitch points between gears 6 and 7 are P6 and P7. And I also gave some names to the points at which the carrier, contacts the gears. So the carrier, when the point where the carrier contacts gears 3 and 4, I call that point A, and the point at which the carrier contacts gears 5 and 6, call that point B. Okay, very good. And then I have a world coordinate system here whose I and K directions are drawn, and the J direction is of course given by K cross I, which means it's pointing outside of the page. Yeah. I also have an origin here, or the point O here, that's fixed on the Earth. We're going to use that. So let's match the velocities at points P2 and P3. Okay, let's do that. So velocity, let's see. Let me put this like that. Okay. So velocity of point P2 in 0, how do I compute that? I take a point that's fixed in the Earth. Let's suppose I take point O, and then I draw a vector all the way to P2, yeah? And then I take its derivative. So, of course, I take the derivative in frame 0, right? That's important. So point O to P2. Okay. So one thing I should notice is that, let's keep that for now. Let's suppose this distance. Let's suppose I know this distance. It will turn out to be immaterial later, but let's suppose that distance is L. Okay, so the position vector that goes from O to P2, of course, is fixed on which rigid body? The second rigid body, right? So what I can do is I can use differentiation in 2 frames formula to differentiate this in the second frame instead. I'm going to use, of course, our usual formula, right? That. Now look, since the position vector that goes from O to P2 is fixed in the second frame, that derivative is 0. Yes? So I'm left with angular velocity of 2 in 0, which I can write as omega 2k, right? It's in the k direction, right? What is the vector that goes from O to P2? Well, I'm going to write it and then explain it. So that vector is R2 minus R3 in the I direction plus some number L in the K direction. Okay, so look at this one. So the I direction, in the I direction I have this distance, right? That distance is what? So sorry, it's not R2 minus R3. My bad, sorry. It is just R2 in the I direction and L in the K direction. So this distance, again, let me draw it again. This distance that goes from here to here, of course, what? The radius of this gear, yeah? So that's R2 in the I direction, yeah? In the K direction, we just speculated that we know that distance, and we said that that's L. And now comes the important bit. Now I'm going to just show you that L doesn't matter. Why? Because this is a cross product right here, right? And I'm essentially I need to distribute this cross product here and there, right? So that's going to be R2 omega 2. Which direction? K cross I. K cross I is J, right? So this is J. But K cross K is 0, right? So L times omega 2 times K cross K, but K cross K is 0, right? So I didn't need to carry this baggage with me, actually. So the distances along this direction doesn't matter when you're analyzing the gears. And when I say this direction, that direction is the axis of rotation of the gears, okay? Good. So I'm going to erase these. And this is the result. This here is the result. Okay. Now, on to the next part, which is the right-hand side of this equation. So, I'm sorry about that. So now I'm going to compute velocity of P3 in 0. Yeah. To do that, I'm again drawing a vector that goes from the origin to now P3. But since I have to use, I have to relate omega 1 and omega 3 to the velocity of that point, what I should be doing instead is I should go from O to A, right? And then A to P3, okay? And if you, of course, add these two pink vectors together, you're going to get a vector that goes from O to P3, indeed. That's what we were looking for, right? So that if you write that explanation in terms of math, what we have is we want to take the derivative of a vector that goes from O to P3, but I'm going to decompose that into two vectors. One of them is O to A, and then the other one is A to P3. Okay? So once you do that, you realize that the vector that goes from O to A is, of course, fixed in the carrier, or the first rigid body in this figure, right? This vector here is fixed in the first rigid body, or the carrier. So what I'm going to do is, when I distribute the derivative over these two vectors, I'm going to go to the first frame to take the derivative of this particular vector. So ROA plus angular velocity of 1 and 0 cross ROA plus, now I'm going to distribute it to this other vector, but this other vector, in other words, the vector that goes from A to P3, right, is fixed on the third rigid body, right? So I'm going to take the derivative in the third rigid body. And this is the usual differentiation in two frames formula. Yeah. Now I realize that this vector, since it's fixed in 1, is 0. The derivative of that vector is 0. The derivative of this vector is also 0 because the vector was fixed in the third frame. Okay. So angular velocity of 1 and 0, let's write that as omega 1k cross. What is ROA? ROA is this vector, and is this vector right there, right? And we just discussed that its component along this direction is immaterial. So I'm just going to worry about its component along that direction. What is that component, if you ask yourself? Well, it is R2 here, right? And R3, and R3, this much is R3, right? So this vector right here, that one has length R2 minus R3. Yeah? So I'm going to write that over there. It has R2 minus R3 distance magnitude, and the direction of it is I, of course. Okay. Plus angular velocity of 3 in 0 is, we can write that as omega 3 in the k direction, cross what's this vector, right? The position vector from A to P3. Again, it has a component in this direction, but those directions don't matter. We just discussed that. So the distance from here to here is what only matters, and that's R3 in the I direction. Great. Okay, so we go through this computation and we find R2 minus R3 omega 1 in the j direction plus R3 omega 3 in the j direction. Right? Very good. So hence this equation here tells us that this R2, the omega 2, is equal to that, which is R2 minus R3 times omega 1 plus R3 omega 3. Okay, so here I'm going to erase all the computations that I've done, and I'm only going to keep this equality here. Okay, I'm just going to keep that. Okay, and this equality came from velocity, matching velocities at P2 and P3. Okay? Great. Now, let's look at the other equality, which is velocity of P4 in 0 must equal velocity of P5 in 0, right? So let's compute velocity of P4 in 0. In order to do that, I'm going to do pretty much the same thing, but in this case, of course, I need to take a vector that goes from O all the way to P4, right? Here. Instead of doing that directly, I'm going to again first go to A, and then from A to P4. Okay? It's for the same reason that I need to express it in terms of the angular velocities of the rigid bodies. If I just went straight over there, that vector is not fixed in one particular rigid body, so I can't just write omega cross R type of expression for it. So what I'm going to do is take the derivative of a position vector that goes from O to P4, but I will be dissecting it into two position vectors, that one that goes from O to A, plus another one that goes from A to P4. Okay, and this one we just computed. What did we find it as? We said that's R2 minus R3 omega 1 in the j direction. This is coming from ddt in 0 of ROA. We just computed that a few minutes ago, so go back if you missed that one. Plus, now I'm talking about the derivative of RA to P4 in the zeroth frame. Of course, the vector that goes from A to P4, this one here, is fixed in what? In the third rigid body, because the third rigid body contains gears 3 and 4, right? So its angular velocity is omega 3 in the k direction. So what I'm going to do is take the derivative in the third frame. Okay? Using the differentiation in two frames formula. Of course, let me carry these terms here. Now, the derivative of in 3 of the position vector from A to P4 is 0 because that vector is fixed in the third frame. Angular velocity of 3 in 0 is omega 3 in the k direction cross our AP4, the position vector from A to P4, component along this direction didn't matter, and the component along that direction is what? R4 in the I direction, right? R4I. So finally we get this to be equal to R2 minus R3 in the omega times omega 1 plus R4 omega 3 in all in the J direction. Great. So we computed velocity of P4 and 0 in terms of the angular velocities of the carrier and the third gear, or the third rigid body, I should say, the fourth gear, which is on the third rigid body. Okay, so now I'm going to do the same thing, similar thing I should say, not exactly the same, but to compute velocity of P5 in 0. How do I do that? Well, in this case, I'm going to go all the way to B first, okay, and then come back to point P5, okay. This way I'm going to relate the angular velocity of this rigid body right there. Let's call that let's say that's the fourth rigid body, okay, that's carrying the gears 5 and 6, but I'm calling it the fourth rigid body just so that the number of rigid bodies are in order. I'm going to relate the angular velocity of that rigid body and the angular velocity of the carrier to essentially the other angular velocities that came from that we used earlier in our computations. So by definition, the velocity of P5 in 0 will be the derivative in 0 of a vector that goes from a point fixed in the zeroth frame to the point P5, right? And again, I'm going to dissect that vector into 2, where I'm going to go from O to B first plus B to P5. Very good. Now, where is the vector that goes from O to B fixed on? Well, that's fixed on the carrier, right? The carrier, this one, contains that vector that goes from O to B. So that vector, since that's fixed on the carrier, I'm going to take that derivative in the first frame. Right? Plus, where is the vector that goes from B to P5 fixed on? Which rigid body? It's fixed on the fourth rigid body. Please don't confuse the fourth rigid body with the fourth gear. The fourth rigid body is the rigid body that contains gears 5 and 6, okay? That's the fourth rigid body. Remember, this one was the third rigid body, okay? So, since this vector B to P5 is fixed on the fourth rigid body, I'm going to take its derivative in the fourth rigid body. Cross our B to P5. Really good. Okay. Now, this is 0, that is 0, by virtue that they are fixed in their respective frames, right, in which we are taking the derivative in. So omega, the angular velocity of 1 and 0 is omega 1k cross the position vector from O to B, right? What's this length right there? Well, that length, I'm ignoring this length again. So now this length here is this length here minus that length there. What's this length? That's R7, right? The radius of the seventh gear. What's that length? That length, that's R6, the radius of the sixth gear. So this is going to be R7 minus R6 in the I direction. Plus angular velocity of 4 and 0, let's call that omega 4 in the K direction. Remember, that's the velocity of the gear 5 and 6. That's the angular velocity of gears 5 and 6. Now omega 4k cross our B to P5. has distance in the I direction r6, so this is r6I. Yeah. So doing this computation will result in r7 minus r6 times omega 1 plus r6 omega 4, all in the j direction. So this matching the velocities at p4 and p5, we get the relationship that this thing is equal to that thing right there. Yeah. So I'm going to write that and ignore all the computation, well, erase all the computation that we've just done, just for clarity. So what we have got is r2 minus r3 omega 1 plus r4 times omega 3 equals r7 minus r6 omega 1 plus r6 times omega 4. Okay? Let's take all these things. Well, let's see. Let's take all these things. Okay, I couldn't take them. Let me try to take them again. Delete. Delete. Oh, yep, that's good. Delete. Great. Before I copy and paste this equality, let me massage it a little bit. This one here, let me massage that just a little bit. Because here, if you can see here, both this and that are include terms omega 1, so I'm just going to combine them. So what we have here is, which side do I want to put them in? Let me put them in, let's move them on the left hand side. So this is going to be r2 minus r3, let's just see, r3 plus r6 minus r7 omega 1 plus r4 omega 3 equals r6 omega 4. Yep. Very good. So let me delete this. Write 4 a little bit more properly. 4. And then put it right here. That's then our next relationship. Okay. The final relationship that we need to work on is that the fact that velocity of p6 in 0 must be equal to velocity of p7 in 0. Well, how do we compute velocity of p6 in 0? Now, I take a position vector that goes from 0 to O to p6. But again, before I do that, I first go to b, and then I go to p6. So, derivative in 0 of a position vector that goes from O to p6. I'm dissecting that into 2, where I take the derivative of our O to b first and then b to p6 next, right? And we just took the derivative of that guy, the position vector from O to b. What did that come out to be? Well, it came out to be what? R7 minus R6 times omega 1, right? That was it. In the j direction. That was it. Then I need to go to p6. Essentially, I need to take the derivative of that guy now. But that vector is fixed in on the 6th gear, in other words, on the 4th rigid body, right? So I'm taking that derivative on the 4th rigid body using the differentiation in 2 frames formula, right? So we get r7 minus r6 omega 1 j plus, this thing is 0, angular velocity of 4 in 0 is omega 4 k cross, what's the radius, the position vector from b to p6, it is r6 in the I direction, yeah, r6I, which will give me r7 minus r6 times omega 1 plus r6 omega 4 r6 times omega 4 in the j direction. All of them are in the j direction. Okay, so let me just a moment, I just want to check something again. Right. So I think I'm, let me see. Did I make a mistake there? Yeah, I definitely made a mistake there. This one should have been R5. And it should have been a negative. Oh. I guess I'll have to redo that. Okay, let me put a reminder here. I'm going to have to redo that. Okay, just bear with me while I finish this equality first. Okay, so this one is that the velocity of p7 in 0 is going to be found by taking the derivative of a vector in 0 that goes from O to p7. Well, that one is simple because the vector that goes from O to p7 has radius r7 in the I direction, ignoring ignoring its component in the k direction. So it's going to be, the result is going to be angular velocity of, let's call this the fifth rigid body. Angular velocity of 5 in 0 across the position vector from O to p7. That's going to be omega 5 k cross r7 I, which is going to be r7 omega 5 in the j direction. So what we have is the equality of these two things. So that gives me r7 minus r6 omega 1 plus r6 omega 4 equals r7 omega 5. Okay, so let me erase all these things. Okay, before I say these are the equations that we needed, I need to double check that equation. So I think I made a mistake when I was computing the velocity of p5 in 0 that I just realized. So velocity of p4 in 0 we found by taking the derivative of a vector that goes from O to A first plus RA to p4. And we said this was r2 minus r3 omega 1 j plus A to p4 is r4 times omega 3 in j. That part is correct, but velocity of p5 in 0 is d dt of a vector that goes from RO to B plus vector that goes from B to p5. Now the velocity of the derivative in 0 of ROB was, what was it? It was right, r7 minus r6 times omega 3, sorry, omega 1 j plus, now the derivative of the vector that goes from B to p5 is actually angular velocity of the fourth rigid body cross minus r5 in the I direction, because this vector actually is not going that way, it's going the back down that way. So this would have to be r7 minus r6 omega 1 minus r5 omega 4 in the j direction. So I need to equate these guys, and when I equate them and put the omega 1 terms on the left hand side as I did before, I get r2 minus r3 plus r6 minus r7 omega 1 plus r4 omega 3 equals minus r5 omega 4, which I hope is the asterisk equation. Okay, indeed it's correct. Okay, sorry about that minus mistake. but the equations that we have on the board after I delete these are correct, and I can now erase that. Okay, so far so good. Now what we need to do is just eliminate from these equations, eliminate omega 3 and omega 4. So I just called this angular velocity of gear 7 omega 7 here, but let's call that omega 5, I guess, since it is the fifth rigid body. So what I need to do is essentially eliminate from these equations omega 3 and omega 4 and get left with a relation between omega 1, omega 2, and omega 5. And that's going to be the end of the problem. Okay, so how do we do that? Well, so one way to do this is just to make them, form a matrix form of the equations and let linear algebra deal with it. Another possibility is solve for omega 3 from here in terms of omega 1 and omega 2, plug it into the second set of equations, and from the second set of equations solve for omega 4 and plug it back into the third equation. And now omega 4 will be a function of omega 1 and omega 2 and various radii. And there you have it. There you will have your desired relationship. I think it is more pain than necessary. So what I'm going to do is I'm going to write a matrix form of the equations whose solution will give you omega 5 whenever you have knowledge of omega 1 and omega 2. Okay? So suppose here I'm going to say I suppose I know omega 1 and omega 2. Then this means the terms with omega 1 and omega 2 will be on the right hand side of an equation of the form a times y equals b. Okay, y will contain our unknowns. So what are our unknowns? Well, our unknowns here is then omega 3, omega 4, and omega 5, right? So I'm going to have a matrix here that's going to multiply our unknown vector, which are omega 3, omega 4, and omega 5. Going to give me some vector that is multiplied by omega 1 plus some other vector that's going to be multiplied by omega 2, right? So let's look at our first equation. Our only unknown in that equation is omega 3. So this tells me put 0, 0, R3 here and equate it. Sorry, totally wrong, because omega 3 is in the first element here. So R3, 0, 0. R3 is going to multiply that. 0 is going to multiply that. 0 is going to multiply that. Yeah. R3 omega 3 is equal to what? Well, it's going to multiply R3 minus R2 times omega 1. Let me make this a little bit larger because I will need it. Omega 1. And then it also multiplies, then plus I have another term, which is R2 times omega 2. R2 times omega 2. Great. Now, the second set of equations, or second equation here, what are my unknowns in this equation? Well, omega 3 and omega 4 are both unknowns, right? What are the so if I put this on the left hand side and then read out, or I just either I put this on this side or I put that on this side. Either way, let me put this on this side and then put this on the right hand side back. So I'm going to read out those equations. Okay, so the coefficient of omega 3 is R4. The coefficients of omega 4, when I put this term on the left hand side, is going to be R5, right? Because minus will become plus. And then there is no omega 5, so I'm going to put a 0 here. And then since I put this thing all the way to the right hand side, yeah, the coefficients of omega 1, which are going to be on the known vector, the known side of the equations, right? It's going to be R7 plus R3 minus R6 minus R2. Yeah, and there is no omega 2 in that equation, so a 0 comes here. Okay. So I'm now looking at the third equation, looking at my unknowns. My unknowns are omega 5 and omega 4. Again, let me this time put this on this side. Yeah, the coefficient of omega 4 in that case is going, well, omega 3 first of all doesn't appear in this equation, so a 0 comes here. The coefficient of omega 4 when I move it on the right hand side is going to be minus R6, right? And the coefficient of omega 5 then is what? R7. Very good. And what is the known vector? It's R7 minus R6 times omega 1. And again, omega 2 does not appear in this set of equations. Well, in this equation. So now you can see here that all of these terms are known, right? And all this vector is all, this matrix is also known. So, and this matrix is invertible as long as what? None of R3, R5, or R7 is 0. Okay? If one of them is 0, then it is singular or not invertible. But if none of them is 0, it is invertible. So you can take the inverse of this matrix, multiply this whole thing by the inverse of that matrix, and find the result for omega 3, omega 4, and omega 5. Great. So that's the end of this this problem right here. I'm sorry that there was a small mistake in between, but I'm going to end this video here and solve the next problem on a upcoming video.